Now let's look at gain control and adaptation in color coding. After we decorrelated these red, green, and blue channels to get these three decorrelated components, luminance, red-green contrast, and blue-yellow contrast, the next step is gain control. We recall that the gain to each channel follows this formula, and in particular, the gain is dependent on the signal-to-noise of each channel. When the signal-to-noise is high, you get stronger gains for weaker channel to enhance contrast, and when the signal noise is low, you give stronger gains to stronger channel to smooth out noise. Now we know that the luminance channel has a signal coming from summing the correlated signals from the three cones, so therefore it has a stronger signal. And the two chromatic channels have their signals coming from the difference between correlated cones, so they have weaker signals. Therefore, when the signals are strong enough, such as in bright daylight, stronger gains are given to these chromatic channels, GRG and GBY, yeah? And therefore, things should look colorful. When the signal is weaker, such as in dim light or evening light, the stronger gains should be given to the luminance channel. G for the luminance channel should be stronger than the G for this chromatic channel, and therefore the visual world will look less colorful. With gain control, this is the response of the luminance channel, and this is the response from the red-green contrast channel, ORG, and this is from the blue-yellow contrast channel, OBY. And this plane, this plane is perpendicular to this luminance channel, and we call this isoluminant plane. That means any vector within this plane have the same luminance value, they just differ from each other in color. Now let's plot out an isoluminant plane. It's two-dimensional with one axis as ORG for the response of the red-green contrast channel, and the other axis as OBY for the response of the blue-yellow channel, blue-yellow contrast channel. So if the response in this plane is this vector, the subsequent visual system uses this response vector to determine the perceived color. So in this case, it's a little bit bluish, a little bit reddish, so its perceived color must be purplish. And if it's pointing that way, now it's bluish and greenish, so it will be cyanish, yeah. Now imagine that you are wearing a sweater of this purple color. Now imagine that the gain GBY along this axis for this output is now suddenly reduced, so that the response O around that direction is just becoming reduced. So this O become O prime, and so this will be the response after this gain is changed. Yeah, in such a case, the perceived color will be less bluish, even though it's still the same kind of reddish. So the perceived color will more look like that, may not be so purple-like anymore. Yeah, and you may ask, well, how can such a gain suddenly get reduced? Well, this could be because the environment changed. Let's say in your environment the signal noise is high enough, in that case the gain usually is inversely proportional to the signal power, or the gain power is inversely proportional to signal power. So therefore, if the signal power in this blue-yellow channel suddenly becomes stronger, then your gain will be reduced. Yeah, and when can this be? This is the blue-yellow channel. That means the blue-yellow contrast variance suddenly becomes stronger. For example, you could be at the disco where there's blue and yellow light flashing a lot, and that will make the signal variance along this axis grow a lot, therefore the gain need to be reduced. And this may explain why things in disco somehow appear in the wrong color. There's a different kind of color than the usual one. And this phenomena is called color adaptation. And this adaptation is a prediction of the efficient coding, because all of these gains and how the channels should be and what that gain should be depends on the statistical properties of your natural environment. And a particular property is the signal power along some of these channels.